Propositional logic. Definition 1. A proposition is a declarative sentence that is either true or false, but not both. And here we have some examples. The grass is green. This is a proposition. This particular grass that I am looking at now is green, so this proposition is true. 2 plus 5 is 5. This proposition is false. In this example, close the door. This is not a proposition. Is it hot outside? This is a question, not a declarative statement, so not a proposition. In the next example, x is greater than 2. Here x means a variable representing a number. So this is not a proposition because the truth value depends on x. For one value of x, it can be true. For other, it can be false. So it is not a proposition. In the next definition, we use letters to represent propositions. If we have two given propositions P and Q, we can form a new proposition simply by putting this word and between, connective, and between P and Q. This way, using two given propositions, we form a third proposition called conjunction of P and Q. The new proposition P and Q has these truth values depending on the truth values of P and Q. Here, in the first two columns, in the first row we have true true, then true false, false true, false false. These are all possible combinations of values of P and Q. And the table gives the corresponding truth value of the new proposition, the conjunction of P and Q. We always use this order of the truth values for two variables, P and Q. Look at the first column, we have TTFF, and then in the second column, TF. We call this the standard order of the truth values for P and Q. And we fix this standard order so that everybody has the same table. Here we have an example. Let P be the proposition, it is Friday. Q be the proposition, the sky is blue. Then the conjunction of P and Q is, it is Friday and the sky is blue. And we continue with this way of forming new propositions. In the next definition, we use the connective or between P and Q. This way we get a new proposition which is called the disjunction of P and Q. And this is the truth table of the new proposition P or Q. This way we denote symbolically P or Q. You see that the first two columns are the same as in the previous table. That is, the truth values of P and Q are in standard order, and then the disjunction is true most of the time. It is false only in one case, when both original propositions are false. we have here in the previous definition, conjunction is true only in one situation, when both original propositions are true. In any other case, conjunction is false. And here we have an example. P means Peter visits us on Saturdays. Q means Peter visits us on Sundays. P or Q then means Peter visits us on Saturdays or Sundays. Another operation that we can apply is negation. If we have one given proposition P, we can form not P simply by putting not before. Or instead of not, we can say it is not the case that P. Not P has the opposite truth value of P. If P is true, not P is false. If P is false, not P is true. In this example, we have a compound proposition, not P or Q. Negation has precedence, priority to any other operation. So first negation must be performed, and then disjunction of the not P and Q. So in this compound proposition, we have two variables. So we have two columns and truth values for P and Q in standard order. Then a column for not P, because first negation of P must be performed. How I fill out this column? Just write the opposite of the truth value of P. TTFF becomes FFTT. And then not P or Q, disjunction of these two. Apply the definition of disjunction. Most of the time disjunction is true. It is false only in one case, when both values are false. So we have false, false here. In any other case, disjunction is true. The next definition is the definition of exclusive or sometimes this is called XOR. It is symbolically denoted this way. And we can read this either P or Q. XOR of P and Q is true in these two cases, when one of the truth values is true, the other is false. In the other two cases, exclusive OR is false. So if both P and Q are true, exclusive OR is false. If both are false, exclusive OR is false. An example of exclusive OR is this. A student can have soup or salad, but not both with dinner. Usually, but not both is omitted, and people say a student can have soup or salad with dinner, and it is understood that it is exclusive or. So in real life, it is not exactly precisely stated what the meaning is. We have to ask. The next operation is conditional proposition. Again, two propositions are given, P and Q, and then you form a new proposition by putting these connectives. If P, then Q. Symbolically, this is denoted this way. P, right arrow, Q. P is called hypothesis or sufficient condition. Q is called conclusion or necessary condition. And the truth table defines the truth value of the conditional proposition. Again, the truth values of P and Q are given here in standard order, all possible combinations of truth values. And the truth value of conditional proposition, by definition, is this. You see, we have three T's. So in most of the cases, the conditional proposition is true. It is false only in one case, when the first value, the value of P, is true, and the value of Q is false. So if true, then false. This is the only time the conditional proposition is false. Here we have an example of a conditional proposition. P means the proposition it is a hot day. Q means I am at the beach at 3 p.m. And then if P then Q means if it is a hot day, then I am at the beach at 3 p.m. When we have a given conditional proposition if P then Q, we can form different propositions from it. One way of forming a different proposition is just swapping the positions of P and Q. If you swap, you get this if Q then P, which is called the converse of if P then Q. It means something else, different proposition. Another way is to swap and then put negations. Not Q, if not Q, then not P is called contrapositive of the proposition if P then Q. Still another way of forming a new conditional proposition from this if P then Q is by applying negations here and here. If not P, then not Q is called the inverse of this conditional proposition. We will see later at the end of the section that only the contrapositive is equivalent to the conditional proposition if P then Q, which means that they have equal truth values for any combination of truth values for P and Q. In this example, if Q then P will be the converse of if P then Q, and it means this: if I am on the beach at 3 p.m., then it is a hot day. So it means something different from this sentence in example 14. Another operation is this. You put, again, you start with two given propositions, P and Q, and form another proposition, a third proposition, by putting this connective between them. If and only if. P if and only if Q. So this is the new proposition. Symbolically, this if and only if is represented by this double-sided arrow. The truth value of the new proposition is given in this table. Again, the first two columns. The truth values are in standard form order, and the biconditional proposition is true only when the truth values are the same of P and Q. If they are different, then the biconditional proposition is false. This is by definition. When you form compound propositions, we may use all these connectives, and in order to write less parentheses, less number of parentheses, this precedence of operators is accepted. Negation has the highest priority, then conjunction, then disjunction, and then implication and biconditional operation. So if you see this expression, it actually means this, because negation has priority. Negation must apply first, then conjunction has priority to these two operations, which means parenthesis here, and then disjunction has priority to conditional operation, so parenthesis here, and then the last operation is the conditional. Example: construct the third table of the compound proposition P if and only if Q, XOR, not P if and only if not R. First, we count how many variables we have. 1, 2, 3. P, Q, and R. 3 variables. So we start with writing 3 columns for P, Q, and R, one for each. And then we have to write all possible combinations of truth values of these 3 variables. And we write them in standard order again. The standard order is this: 4 T's for P, 4 F's for P, the first variable. For the second variable, 2 T's, 2 F's, 2 T's, 2 F's. For the third variable, TF, 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 TF. So this is the standard order. And we have here how many rows? These are 8 rows, which is just 2 cubed. 3 variables, we have 2 cubed. 8 rows in the table. It must be always like that. and the standard order must be always like this. Then we look at the given compound proposition. Here we have parentheses, so we have to open a column for P if and only if Q. In the beginning, the column will be empty, and we just fill it out using the definition of biconditional. The values of P and Q come from their column, the first two columns. In the first row, we have two T's, so biconditional is true. Second row, two T's, true. Third row, TF, different values, so biconditional is false, 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 false. Here the values of P and Q are equal, so the biconditional is true. And in the last row, P and Q have equal values. This is true. Then we look at the next part of the compound proposition. We have these parentheses, and inside not P. Negation has priority, so I write a column for not P. In the beginning it will be empty. How I fill it out? You look at the values of P and write the negated value. In the first row P is true, so not P will be false. And you continue like that. Then write a column for not R. The values of R come from here, the column of R, and you fill out the rows of not R of this column. This is the negated R. In the first row R is true, so not R will be false. And you fill out the whole column. Then we can write a column for the expression in this parentheses. It will be empty first, and you fill it out. How? You write biconditional of these two values, the value of not P and the value of not R. In the first row, we have two F's, equal values, biconditional is true, by definition. In the second row, not P is false, not R is true, different values, biconditional is false. And we continue like that to fill out the whole column. And finally, we write a column for the expression of the problem. Yeah, first it is empty. How we fill it out? We look for values of this in its column and for value of this expression in its column. In the first row, we have two T's, so the result is F. And we continue like that. In this example, we show that the contrapositive is equivalent to if P then Q. We have only two propositional variables, so the number of rows will be 4, which is 2 squared. Fill out the first two columns in standard order. If P then Q, these truth values come from the definition of conditional proposition. Then fill out not Q, the column of not Q. The values of Q come from here. Not Q is the opposite of Q. Q is true, not Q is false. Fill out the column and write a column for not P. First it is empty, but then we fill it out by looking for values of P from its column. P is true here, not P will be false. And you fill out the whole column. And then a column for the contrapositive. First it is empty, then we look for values from the columns of these two. Not Q is false in the first row, not P is false. By the conditional proposition is true. You know, conditional proposition is false only when we have if false then true. If false then true is appears only. It is false only when the first is true and the second is false. So only here in the second row. In any other case, it is true. And then we compare the columns. This column, the column of the conditional proposition, and the column of the contrapositive proposition, they coincide, they are the same. That's why the contrapositive is equivalent to the biconditional proposition.